Good afternoon. Good afternoon, and welcome to the Concrete Institute of Australia. I'm John Nichols, Technical Manager for the Institute. It's my pleasure to be your host for this afternoon's webinar on CIA NEXGen Cement and Concrete Pathways to Net Zero. This webinar is one of the CIA NEXGen webinar series. CIA NEXGen is organised, hosted and presented by members of the CIA Young Professionals Group. Today's webinar will be hosted by CIA New South Wales Young Professional members, Josh Tapas and Sophie Maguire, and will focus on the cement and concrete pathways to achieving net zero CO2 in the concrete industry by 2050. Our speakers today are Jerry Fu and Olivia Alexis. I'd now like to invite one of our young professionals, Sophie Maguire, to say a few words on behalf of the CIA Young Professionals Group. Sophie?
Thanks, John. So the Young Professionals Group aims to engage the members of the young professionals within the Concrete Institute of Australia and encourages their involvement within the organisation through collaboration, building networks and connections, helping to organise events and activities, and liaising with other young members. It's free to get involved with the Young Members Group. There's a button on our website where you can join up. Just helps to make friends, get to know people, and get to know people in other states, different careers, different career paths, and just what else there is out there. So if you want to get involved, feel free to touch base with Josh or I, or just press the Join the Young Professionals Group on the website. Thanks, John. And now I'll pass it over to Josh to introduce our first speaker. Thanks, Josh.
Thank you, Sophie. It's my pleasure to introduce our first speaker for this afternoon, Dr. Jerry Fu. Jerry is a material scientist in Boral Innovation. Jerry completed his PhD at the University of New South Wales on developing high-performing concrete with high levels of clinker replacement via investigating pore solution chemistry and microstructural development. His research area of interest is exploring the synergy of cement chemistry and microstructural development of the next generation concretes using construction and demolition waste and alternative SEM for clinker substitution. He also has published peer-reviewed publications in cement and concrete research. His presentation is entitled Turning Australian Recycled Aggregates into a Permanent Carbon Sink via Accelerated Carbonation. Ladies and gentlemen, please join me in welcoming Jerry.
Thank you, Josh. Hi, everyone. My name is Jerry Fu. I'm very glad to be invited by CIA to present on the topic of pathways we're planning to take to help us achieve net zero goal. So my topic today is on using recycled aggregate as a potential source for long-term CO2 storage. So many of us have already heard that cement production is responsible for about 7% of global anthropogenic carbon emissions. More than half of these emissions are due to the release of CO2 upon the thermal decomposition of the raw material we use, limestone, during cement manufacturing. This chemical decomposition process contributes to about 60% of the total carbon emissions of the cement manufacturing process. At the same time, the fossil fuel used during the manufacturing of cement accounts for the other 40%. For every ton of manufactured grey cement, about 700 to 800 kilos of CO2 will be released. As long as we don't change the raw material we use to make our grey cement, CO2 emissions will be unavoidable. To manufacture cement, the powder raw material is fed into the preheater tower and then the calciner. It gets heated and the calcium carbonate, the limestone in the raw material undergoes a calcination process. The preheater will consist of a series of cyclones through which the raw material is heated with the hot flue gas, and the calcination of limestone will take place at around 900 degrees. The chemical process will can be described as CO2, calcium carbonate transforming into calcium oxide and CO2 gas. And a portion of that calcium oxide will be released, reacted with silicate materials in the calciner, especially when that raw material particle contains both lime and silicates that are in direct contact, resulting in the formation of belite and some aluminate and ferrite phases. The unreacted calcium oxides will be denoted as free lime. The calcine raw material then enters the rotary kiln, where the main clinker phase, alite, is sintered to a temperature of 1400 degrees Celsius. And this is why the manufacturing of clinker is so carbon and energy intensive. So we need a greener way of making and using cement in this era. The industry aims to strive towards a net zero carbon emission target by the year 2050, even as the industrial demand is growing and we have energy prices soaring as we in today's market. So for the past decades, a lot of effort have been put into developing new binders to substitute Portland cement to create low carbon blended cement systems. Further research has been done and continue to investigate and develop new technologies to help mitigate operations and manufacturing carbon emissions. Technology including the new approach to limestone calcination, burning waste products to power the calciner, and pumping CO2 deep underground for permanent storage. Even though everyone is working incredibly hard to minimize our carbon emission as much as possible, but a considerable portion of CO2 emission generated in cement manufacturing is unavoidable. It cannot be tackled using established techniques such as alternate fuel or clinker substitution. So we must continue to develop new technology that prevents CO2 from reaching the atmosphere on a large scale by investing in long-term storage solution in the realm of carbon capture technologies. One way to store the CO2 in our concrete material can be done by a process called carbonation. So recycled concrete contains alkaline minerals in the attached mortar that is ideal for carbonation and then used as upcycled aggregates in concrete, preserving our natural resources. This process works by having cement hydrated products gradually reabsorb CO2 from the atmosphere through a physiochemical process called carbonation. During the carbonation, CO2 diffuses into the pores of cement-based materials and reacts with hydrate products such as Portlandite and CSH in the presence of this acidified pore solution. The carbonation starts at the surface of the concrete or mortar and slowly moves towards the core of the material. And this carbonation process is also influenced by a range of different influential factors such as CO2 concentration, hydration product compositions, and exposure time. This process is a natural process. So carbonation is a natural process, but the problem is it's a very slow occurring process. It's been reported up to 50% of our CO2 emissions from the clinker manufacturing process can be reabsorbed by the concrete structure over its service life. There is an extensive need for aggregates in the production of concrete and other construction material due to the large number of construction projects occurring worldwide and also here in Australia. Therefore, there is a business case that we can for encouraging recycled facilities as well as construction material manufacturers like Boral to source a part of our need for aggregates from recycled materials. According to the 2020 National Waste Report, Australia produced about 27 megaton of C&D waste, which is about 36% of the total waste we produce. 23% of the waste was disposed either as landfill or destroyed. 76% was recycled and 0.7% was recovered for energy at the landfills. Usually after demolition of old roads and buildings, the removed concrete is often considered worthless and disposed as demolition waste. By collecting the used concrete and break it up, recycled concrete aggregates is created. Recycled material used to produce construction aggregates for concrete comes from two primary sources. So the first one is road construction and maintenance debris, and second is structural constructions and demolition debris. So for example, we're talking about demolished buildings, bridges, and sometimes roads. Most of these recycled materials go through the process of recovery. So that's your demolition, breakage, and collecting. And it gets transported to a local collection point. Then it gets processed. That process entails crushing, screening, and separating and stockpiling before it gets marketed as sized products for multiple use. So the construction demolition waste could contain wood, plastic, gypsum, metal, glass, and paper, which can be removed at the plant. Other materials that can be preserved or that can be present, maybe mortar paste, bitumen, bricks, tiles, and rubber. So the C&D waste is crushed and sieved into different size fractions. The ones that the recycled aggregates produced at recycling plants may contain 65 to 70% coarse and fine aggregates, while the other 30 to 35% will be adhered old residual cement paste. The amount of cement, mortar paste or cement paste is reduced as the number of crushers increase, but this usually incurs more production cost. Unfortunately, we can't just simply swap out the natural aggregates for recycled concrete aggregates. There are some significant differences and drawbacks regarding recycled concrete aggregates. After crushing the recycled concrete down to different aggregate sizes, the process can introduce microcracks within the residual mortar and weaken that bond between the original aggregate and the old mortar. So aggregate cement interfacial zone consists mainly of these loose and porous hydrates. Since the difference in properties of recycled aggregates with respect to natural aggregate is mainly driven by the presence of the old attached mortar to the surface of the recycled particle, the residual mortar is responsible for the lower specific gravity, high absorption, and low abrasion resistance for these recycled aggregates when we compare it to natural aggregates. These residual adhered mortar on aggregate is a main factor affecting the property such as density, porosity, and water absorption of recycled aggregates. The density of these recycled aggregates is generally lower than natural aggregates. This is due to the adhered mortar that is less dense than underlying natural aggregate. The variation in density can depend on the specific aggregate in question. The adhered mortar can be a lightweight compared to aggregates of the same volume, which cause a decrease in product density. The residual mortar on the recycled aggregate have greater porosity. This allows the aggregate to hold more water in its pores than the natural aggregate. The lower density and high porosity, this can lead to a reduction in the durability of the final concrete product. Literature suggests that the construction demolition waste aggregate contains about 0.1 to 0.3% higher chlorides and sulfate than this natural aggregates, while the recycled aggregates have a higher abrasion. However, on average, they are still suitable for both concrete use and roads. Another thing literatures have suggested is that recycled aggregates have approximately 50% lower crushing values when compared to the natural aggregates we've been using. But all the literatures have suggested that recycled aggregates were suitable for non-structural, to be used as non-structural aggregate, or suitable for minor structural elements. Since the surface of the recycled aggregate is attached to a large amount of aged cement slurry, this will increase the number of pores and cracks, resulting in lower workability and lower mechanical property of the recycled concrete compared with natural concrete. So, for example, the higher water absorption of aggregates leads to reduced workability of concrete, thus making concrete difficult to be pumped. Compressive strength decreases as the content of recyclable aggregates increase. This is for both coarse and fine aggregates. Therefore, a good mix design and preparation of these aggregates are needed to be maintained at maintained to produce high quality concrete. As we have mentioned, that recycled aggregates have lower density and high porosity. These can lead to faster iron ingression. The high porosity of both these, the fine and coarse recycled aggregates allow gases to permeate more easily through the concrete internal matrix. So I'm going to go through the rest of these issues that's listed on the slides due to the time limit. So given the subpar performance of recycled concrete aggregates, also partially depending on this partially depends on the historical usage and the way it was reclaimed. Customers of such products need to know whether it is safe enough to be used in the projects. So the drawback of using recycled aggregates in concrete helps to identify some of these minimal performance specifications that the aggregates and the concrete needs to achieve before it is deemed to be good enough to be used in non-structural or minor structural elements. There are two of these documents that I'm providing here that help to set clear guidelines around the minimum specification recycled aggregates need to meet before being used in specific projects. So one from the Department of Environment, Climate Change and Water, New South Wales, as shown on the left, and the other one from Standards Australia, which is shown on the right. So for instance, the specification for the supply of recycled material for pavement, earthwork and drainage 2010 document provides performance standards for the supply of quality recycled material to increase confidence in the marketplace, and also legal requirements for recovery and reuse of construction materials and guidelines for placement of pavement material to ensure the compaction necessary for design performance. So beyond these two documents, there are Transport for New South Wales, Queensland's Department of Transport, and the main transport departments of transport and the main roads, and Vic roads have all published technical specifications for concrete that wants to incorporate recycled aggregates. These specifications entails the tests one needs to perform on the material, all the way down to specifying their applications. So similarly, the required specifications for employing recycled aggregates are also outlined in different standards, such as the American ASTM and British BSEN standards. So at the end of the day, these documents are here to provide a more comprehensive understanding of these types of waste and byproducts material in construction application, and provide general guidance on engineering evaluation, and entails some environmental issues and economic considerations. These documents also consolidate the available materials for technical consideration and provide product specification informations and tools for conventional designs. So despite the performance limitation of recycled concrete aggregates, the material has been used in various construction projects worldwide in countries in Asia and Europe. Projects range from residential building to industrial buildings. It is nice to see recycled aggregates not used just as road-based material in projects. So we know it is a viable source of construction material. It just needs more further property enhancement to unlock its full potential. So we are determined to reduce our CO2 emissions at Boral and capture CO2 from our cement plants. This also helps our industry to move closer to its net zero target by 2050, whether it is to use a combination of decarbonisation techniques such as calcium looping or post-combustion technology at existing cement plants for carbon capture. We need to prioritise our on-site CO2 utilisation before moving to underground storage afforestation, or passing it on to our downstream customers. To achieve that, one of the methods is to utilize a CO2-rich or lean flue gas to accelerate the carbonation of recycled concrete aggregates to sequester the CO2 and to improve the performance of our recycled aggregates to overcome its inherent shortcoming that was mentioned earlier in this presentation. It all started with small-scale laboratory tests at Boral and the lab in UTS. We are continuing these tests on our carbonated concrete recycled aggregates to assess its strength and durability performance compared to the additional GP cement mix designs. And we're still running ongoing experiments and trials in our labs to optimize the ideal condition for our recycled material. We use thermogravimetric analysis and X-ray diffraction to perform the initial analytical analysis to see the effectiveness of the carbonation reaction and compare rates of carbonation reactions. We use our in-house carbonated recycled aggregates to conduct concrete trials to investigate the performance of our products at various natural aggregate replacement levels. So far, our preliminary results have shown to be in alignment with reported results from the literature. We're still doing more experiments, working to optimize the carbonation parameters further to maximize the CO2 uptake of the by recycled concrete aggregates to help us to push the limit of replacement boundaries. So this project is a collaboration between academia and the industry. University of Technology Sydney provides a crucial role in providing technical expert supports. The federal government provides funding to Boral and UTS through the Carbon Capture Use and Storage Development Fund. The supports allowed us to demonstrate the viability of this process by building a pilot plant at Barramar Works and utilizing the upcycled products to perform concrete trials. The upcoming objective is to complete a pilot trial and the construction of a pilot plant by the end of the second quarter of 2023 and start bulk carbonation on site using the redirect flue gas from the main stack at Barramar Cement Works. We'll transfer the knowledge we've gathered from our laboratory test and to optimize the carbonation condition that is most effective and efficient for the pilot scale and eventually scale up to a commercial scale. So to wrap up this presentation, I would like to say how incredibly excited we all are at Boral to be carbonated locally sourced recycled waste concrete, adding value to what once was an industrial waste product that will go straight into our landfill. Like everyone else, we are working very hard to achieve our target emission reduction goals and are all doing what we can to contribute. Well, this project is only the second attempt of its kind in the world. And at Boral, we are very proud to be the first to carbonate using redirect flue gas in Australia. We are very excited to start permanently locking away some of our CO2 emissions. Thank you. I hope you have enjoyed this presentation. If you have any further questions, feel free to contact me.
And ladies and gentlemen, I ask you to join with me in thanking Jerry for a very interesting presentation. I'd now like to invite Sophie Maguire to introduce our second speaker. Sophie?
Thanks, John, and thanks, Jerry. So Olivia graduated from the Queensland Uni with a Bachelor of Engineering in 2020. Her interest in civil materials led her to working at Cement Australia during her last semester of uni as a technical services graduate. Commencing as a technical product specialist in late 2020 at Cement Australia, her role involved the quality control of Cement Australia's bulk materials, technical customer support, trial work, and R&D, work with a focus on alternative SCMs. Her work in this field has led to this beautiful presentation about reducing embodied carbon in cement and concrete. So thank you, Olivia.
Perfect. Thank you so much, Sophie. So today I'll be talking about reducing embodied carbon in cement and concrete. So just the agenda today, I'll talk about the purpose of alternative binders, and then I'll mention about readily available binders versus potential binders. I'll also just give a brief overview of Cement Australia's carbon roadmap, and then I'll be able to answer that question as to whether or not we really do need alternative binders. I'll also talk a bit about the future of cement manufacture, and then I'll close off with a summary. So, what is the purpose of alternative binders? How did we even get to this point that we are investigating alternative binders? So for the last decade, if not more, we've been using conventional supplementary cementitious materials, SCM, such as fly ash and slag, for two main reasons. One of them being for durability purposes. For instance, fly ash helps mitigate against alkali silica reaction, ASR, but also we've implemented fly ash and slag into concrete mixes to reduce the embodied carbon in concrete. That said, we're not always going to have fly ash and we're not always going to have slag. If we take slag, for instance, when we look at the freight and the complexities of logistics, or maybe even the increase in cost materials, we have to understand that even now, as it's becoming quite scarce for us to actually attain some slag material, actually import it into Australia, it's going to come to, we're going to get to a point where we're not going to be able to actually use slag in our mixes because of these limitations. Or if we look at fly ash, the closure of power stations, if we look at, say, Eraring moving their closure date to the next 5 years, we won't always have the virgin fly ash that we currently use in concrete to reduce our carbon emissions. So we'll need substitutes. And so that's when alternative binders will come about in order to maintain low carbon concrete mixes. So just a few examples of some alternative binders. I've named a few, but there are still a lot being developed and a lot that I haven't mentioned yet. But some of these are dam ash. We have lithium byproducts, so the waste of the lithium industry. We have recycled concrete. We have calcined clay that I believe a lot of people have heard of. We have volcanic ash, and we also have red mud. So red mud is the waste of the aluminium industry. So the way in which alternative binders will be prioritized or that I've named a few. So if we look specifically at dam ash, or if we look at calcined clay, you can compare the two and say that dam ash will be a more viable alternative binder. For one reason in particular, it's because it's a readily available binder, and it will have low energy in order to process it when comparing it to, say, a calcined clay. To process calcined clay, there's a significant amount of low investment costs, and it wouldn't necessarily be upholding that circular economy when comparing it to dam ash, whereby the material is just in the dams, or for instance, looking at red mud, whereby you're using a waste material and you're recycling that. So that is what upholding a circular economy is. So if we look specifically more into a readily available binder such as dam ash, I've considered dam ash to be readily available for one particular reason, and that is because the material is there in the ground and can easily be reclaimed, or can easily be processed at a very much low investment cost. So the material basically needs to be taken from the ground, dried and milled. So just a bit of a background on dam ash. there is an extensive amount of fly ash and bottom ash in dams alongside, right next to a lot of power stations. So power stations for years have been pumping bottom ash and fly ash in dams for many years for different reasons. Some of these reasons could be high LOI that doesn't necessarily meet the requirements, or it could just be a lack of space and having to put it into dams. For some of the power stations that are currently closed, those dam ashes have actually been capped over. Some have just been, there's been vegetation that has just grown over, but the material is still good and can still be used. In some applications, the depth is unknown and the quality may vary, but overall, I still believe that dam ash would be a more viable alternative binder. Some limitations to the use of dam ash, one in particular is some dams have sluiced the water that they pump the ash into, the ash from the power stations to the dam with salt water. So this would be quite detrimental if we're looking at the chloride percentage. And some may say you can just wash the dam ash in order to reduce that chloride percentage. But when we're going back to what is a more viable alternative binder, we want to reduce our investment costs. We want to reduce the amount of processing that we need in order to obtain this material. So we would more likely focus on ash dams that haven't been sluiced with water prior to looking at other dams that have been sluiced with salt water. Another limitation that I already mentioned was certain dams have been capped. So these are just a few power stations, well, all the power stations in Queensland, and I've just put a few pictures up just to really show how large these dams are and how much material, how much fly ash, how much bottom ash is in these dams. So currently in Queensland, the power stations that we have are Gladstone, we have Tarong, Swanbank, which is currently closed, Kogan Creek, Stanwell, Millmerran, and Calais. So if you look in this picture, it really does emphasize that a material like dam ash is readily available because the material is right there and it needs minimal processing. When we're comparing something like dam ash to, say, calcined clay needs a significant amount of processing. This is why I've considered calcined clay as a potential binder. It doesn't mean that it can't be used as SCM, it just means that it needs more investment and it needs more processing in order for it to be used as an SCM. So just a bit of background on calcined clay. There is an extensive amount of clay deposits across the world, and that could be kaolin, could be MMT, serpentinite. A lot of the work around calcined clay has been focused more on kaolin, mainly because the gel structure of kaolin research and also trial work has also shown that this is a more viable clay material to use compared to some other materials, but there's still a lot of research out there being investigated around materials such as smectite. However, the chemical mineralogy of a specific clay, whether it's kaolin or smectite, really does determine whether or not or how much it is pozzolanic, how much it is reactive when it comes to being a pozzolan. One particular application of calcined clay is LC3 cement. So for those who don't know what LC3 cement, it is a product that is being currently developed or investigated. So it's not yet a product, but it's something that's being investigated in Europe. It is a limestone, clinker, and calcined clay cement. So this is one possible application that calcined clay could be used in. But just to emphasize again, I would say the biggest limitation when it comes to calcined clay, and limitation in the sense that it requires more energy compared to dam ash, is that it would need a flash calciner or a rotary kiln for that calcination process. So it kind of leads on to the limitations of calcined clay. I've already touched base on the amount of cost and the space that would be needed in order to process clay as a means of producing calcined clay. But I really need to emphasize on the lack of space, because currently in Australia, the few kilns that we do have are already being used for the manufacturing of clinker. And some may question, why can't we alternate between the two, between producing or manufacturing clinker and then producing calcined clay? But it's two different animals, and you can't alternate between the two. You would have to invest in a new rotary kiln in order to calcine clay and produce calcined clay in bulk, which would be quite expensive. Another limitation is color. So as many of you may or may not know, clay, a lot of the time, if we look specifically at kaolin, is very rich in iron. And so during the calcination period, you will see that there is a change in color in the clay, and it becomes a nice warm red. So this could be a limitation when it comes to using it in concrete. However, there are methods like monitoring the cooling or other methods that could be used as a means of reducing the redness in concrete. One other limitation would be implementing and educating of a new SCM. So this is inevitable when it comes to implementing new binders in the industry. A lot of people, whether that's industry, whether it's the market, are always going to be hesitant or skeptical. And that's, I guess, the benefits of dam ash, because we have a lot of data, a lot of trial work. When it comes to fly ash, it's a little bit harder for something like calcined clay to be accepted into the market. But this is something that we will work on even when it comes to additional testing or the increase in quality control. It's inevitable that there may be a little bit of pushback in the market. And though this limitation might be minor, it's still something we have to consider. Another limitation would be inflated costs due to the lack of production and processing plants. And just lastly, possible compliance limitations in AS 3972, which is the cement standard. So currently we have a pozzolanic standard, so the manufactured pozzolans, which is AS 352. Part 4. And so right now it's not mentioned in the cement standard. So this is a limitation, a current limitation, but that's not to say in the future, well, in the near future, it will be changed and it will mention the new manufactured pozzolan standard. So now that we understand, I guess, what alternative binders are, the purpose of them, and just some examples of them, this is just an overview of Cement Australia's carbon roadmap. And I understand that all industries and all companies have their own goals and achievements that they want to, but that they're moving towards, their objectives that they're moving towards reducing their embodied carbon before 2030 or even 2050. So if we look at this carbon roadmap, we believe that we'll have fly ash and slag up into 2040. And that's just going off, say, the closure dates of power stations. We might have lithium byproducts that will kick in after 2025, and that will be more Western Australia centric. But as that comes online, that should assist with elongating the lifespan of slag. And then we'll probably have some readily available binders such as dam ash that could come online just before 2035. And then most importantly for Cement Australia, we have green methanol carbon capture, which I will talk a bit more in detail later on in this presentation. And that will be a really important period for us In fact, it will be, and it is the long-term solution to low carbon concrete, and we'll be able to reduce embodied carbon when it comes to cement manufacturing to zero, to nearly zero. So the question is, when then will we use other alternative SCMs? And they may kickstart in 2040. As we would be able to produce a cement of zero embodied carbon, we'll still need alternative SCMs for durability purposes, such as ASR mitigation or other reasons. But the question still holds, do we need alternative binders? Should we still look at alternative binders? So this is just a typical kind of breakdown of a concrete mix. We have GP cement, so general Portland cement. We have coarse and fine aggregates, and we have our SCMs, our conventional SCMs such as fly ash. As you can see in this pie chart, GP cement is approximately 80% of the embodied carbon in the constituent of raw materials, which is very significant. So if we look specifically at numbers, GP cement, when it comes to embodied carbon per ton or CO2 emitted per ton, is approximately, and this is just a generic number, is 0.8820. When looking at fly ash and slag, fly ash is 0.027 and slag is 0.143. So they are significantly low when compared to GP cement. And this was the reason why fly ash and slag was introduced into concrete, was to really reduce this number here, which is the GP cement content. However, when we no longer have fly ash and when we no longer have slag, we'll need to have other substitutes that will ensure that this GP component of 0.82 remains low in concrete. However, when it comes to Cement Australia, as we'll have our green methanol coming on board, this 0.82 will actually reduce to zero or close to zero. And then the question will be, will we even need to have a high percentage of alternative binders in concrete mix designs? So just to explain what this green methanol that I've mentioned a number of times in this presentation is, so Cement Australia has partnered with Mitsubishi Gas Chemical Company to make green methanol. So just a bit of background on the process of green methanol. So the first stage of this process is electrolysis. So basically through the use of renewable energy, say solar energy, an electrical charge is passed through water, which separates the hydrogen and the oxygen. That process there is called electrolysis. And because we use renewable energy, the hydrogen would be considered as green hydrogen. So then the second phase to this process is using the oxygen and using that in our kiln instead of the air that we currently use. And the oxygen will be used to enrich the burning environment of our kiln. Then we'll be able to capture a high purity of CO2, and we'll provide that to Mitsubishi. So with the use of green hydrogen and CO2, that then will produce methanol. And with the use of green hydrogen, it's actually now green methanol. And for those who don't know, methanol is a building block for many things, whether it's pharmaceutical drugs, just a number of things that it can be used for. So at Cement Australia, we are very focused on capturing our CO2 as a means of reducing embodied carbon, reducing the reliance on SEM. And the question is posed again as to, do we need alternative binders? So we still believe that we'll need alternative binders when it comes to the durability side of concrete, such as ASR or other things like that. But for Cement Australia, we're very focused on reducing our embodied carbon in cement manufacturing through the use of green methanol. So just in summary, driving embodied carbon contents downward in concrete mixes continues to be the primary focus of current and future R&D. Alternative binders could be used to replace conventional SEMs such as fly ash and such as slag, and reducing embodied carbon in cement manufacturing can be accomplished through the production of green methanol. Thank you for listening to my presentation.
And thank you, Olivia. Ladies and gentlemen, I'd ask you to join with me in thanking Olivia for a very interesting presentation. I'd now like to invite the speakers to turn their cameras and microphones back on again. And now I'd like to invite Josh Tapas to present the questions and answer sessions.
Well, again, thank you very much to Jerry and Olivia for those presentations. So Jerry basically talked about carbon capture in recycled concrete aggregates, whereas Olivia talked about alternative binders, as well as the use of green methanol as a future for cement manufacturing. So I guess I'll go to Jerry first for the Q&A. We have a few minutes to go through some questions. For Jerry, this is from Stefano Bosch, and I know that you've answered it already here, but just for the sake of everybody listening to the webinar, there's a question as to whether there has been any applications of the recycled concrete aggregates for primary structural concrete elements in Australia.
Thanks for the question. Like in Australia, recycled carbonated recycled aggregates haven't really been used for primary, well, talk about primary structural elements, because it's still a relatively new concept that people are testing. So we have recycled, as in for recycled aggregates, not even the recycled uncarbonated materials have been really used in primary structural due to its limitation and drawbacks in terms of its performance. These shortcomings can be improved by the carbonation process, but we are definitely not at the moment ready to use it as a primary structural elements when we compare it to the performance of natural aggregates. Possibly for minor structural elements, it might be possible in near future, but primary not yet.
Yeah, just a follow up on that as well. So basically this project is hitting two birds with one stone, capturing CO2, while at the same time enhancing the mechanical properties of the recycled concrete aggregates, right? Could you probably just, because we're building a pilot plant and all that, could you potentially elaborate more on the more challenging aspects of the project?
Oh, one of the challenge, or there are numerous challenges in this process. One is definitely optimizing the process, the carbonation process. It's difficult in a way because it's influenced by so many external factors. And this process, it's a long, continuous process because it depends on the source of your material. As we know, recycled material at a recycling facility, it does not come from one stream. We're collecting material from multiple streams. It does not necessarily from Borrow itself, ourselves, but also from other concrete providers. So we have little knowledge in terms of what type of material is arriving at our site. So you have it's quality control as it can be challenging. So we are looking at, so a lot of literature is based on demolition waste. So these are, we're talking about old concrete mixes that are generally straight GP cement. But then we also can be looking at potentially concrete truck washouts, return concrete waste, which are relatively new mixes with components of SEMs. So we're talking about fly ash and blast furnace slags, incorporating in a mix of GP cement. So that variation in its the mix design changes the cement chemistry and its phase assemblage, which will cause more challenges when it comes to the process optimization.
Thank you, Jerry. I'll probably jump on to Olivia first. In the interest of time, there's a question from Jason Chandler of Borla Innovation. It says, Olivia, are you able to elaborate on the concentrated CO2 capture in the kiln stack? Is the plan for it to be concentrated further or use the flue gas as is? So.
Thank you so much for your question. So currently what we're capturing is around 20% CO2. So with the use of oxygen to enrich our kiln, we actually be capturing around 85%. So that's what we'll be aiming towards. And that's what we'll be actually be capturing.
Okay, thank you. There's also another question from Sebastiano Bianchini. I'm not sure if it is something that you have, at the moment, but it's asking what is the energy balance in the production of methanol for hydrogen and carbon dioxide? Not sure if it's very technical question.
So, I think what you're referring to, and correct me if I'm wrong, and I apologize if I am wrong, but what we will be using during the electrolysis process is 100% renewable energy. So I think that's what they are referring to.
Yeah, I'm not very sure as well. We'll probably give Sebastian a chance to clarify the question further. In the meantime, I'll jump into Jerry for now. There's a question, Jerry, you've mentioned Boral was the second company to introduce carbon dioxide into recycled aggregates in the world stage. Do you know who is the first one?
I believe it's a Swiss company.
Okay.
It's a startup who utilized CO2, and they produced their materials within like a custom reactor. And they've been I think they've been looking for, or they have been partnering up with a cement company or a cement material company to do trials. So I think they're probably the first in the world to start carbonating recycled aggregates.
Thank you, Jerry. And just coming back to Olivia again, so you've mentioned green methanol. It's actually my first time hearing this actually as a process for cement manufacturing. So would you be able to elaborate whether this is technology that has been explored in other parts of the world? And then Cement Australia is adopting it here?
Yes, that's correct. Sorry. So Mitsubishi has partnered with numerous companies across the world. So it's not necessarily a new method in which you can produce green methanol, but it's something that will be first to Cement Australia. So no, it's not necessarily a new method of producing green methanol. It is being done by Mitsubishi Gas Company across the world.
Right. Okay. Thank you. And you've also talked about alternative SEM, such as red mud, lithium byproducts. So Cement Australia is carrying quite a lot of work on this at the moment. Is that correct? Exploring.
Yeah, that's correct.
Okay.
I think it's important to explore numerous alternative binders, because I think we have to all understand that we're not going to have fly ash and slag forever, and we're going to have substitutes to fly ash and slag as a means of maintaining low embodied carbon in concrete, but also maintaining the durability characteristics of concrete. So yes, we've done a lot of work around alternative binders and investigating them in concrete and how they work.
Thank you, Olivia. Question again for Jerry from Liang Li of CSIRO. It says, for accelerated carbonation of RCA, which carbonation treatment seems more attractive in the industry? Is it gas solid or aqueous carbonation, and why?
This is a hard question.
Yeah, it's a bit more. Yeah.
I think in some literatures they have done some comparison between the two methods. With with us, we are at a stage of trialing gas solids, but we are keeping our options open. But at this stage, they have reported early acceleration and carbonation in the liquid-based method. But I think that limitation could just be just at an early stage. So for the ease of carbonation, I think, I think I'll probably lean towards gas and solids. It's very dependent. I guess it's a hard question because it really depends on the type of materials you're getting, the type of cement that's being used, and as we move into, more of relatively newer mixed designs with a higher percentage, high SEM, high clinker replacement with various SEMs, there will be a change that will be noticed and impacting our carbonation process due to its microstructural change. And as we know, high SEM have better durability due to the refinement of pore size, and so that could restrict access by either solids or liquids. So it's a hard question to have like a pinpoint on which is better. There's just too much influential factors that's going to contribute to answer what's best for you.
Yeah, and that probably also answers Ruben Ramsey's question from Maclay Industries. So the question is, has there been any work done to improve the ITZ from the RCA and the paste? And if so, what has been done?
Yeah, so this ITZ is a crucial factor that you have to consider when you look at performance of your recycled aggregate, especially when there's going to be forming a new ITZ zone on top of what the existing original ITZ between the original natural aggregate and the old adhere paste. So our test is still ongoing, and we're assessing the long-term effect and performance of from our concrete trials. So it's definitely something we're testing, and there's still results coming. So it's within our experimental scope and optimization to find the right mix to achieve the maximum replacement of natural aggregates with treated carbonated recycled aggregates to minimize our carbon footprint.
Thank you, Jay. I just jump onto Olivia again. Ruben has another question. Ruben from Maclay Industries. He's asking, Olivia, what is the estimate of which fly ash and slag will run out or become very hard to source? I think this was in your presentation.
Yep, that's correct. So in my presentation, I mentioned on our carbon roadmap that we said 2040. So different power stations, their closure dates range from 2025 to 2035 to 2040. So I've just said 2040 as kind of like the maximum date. But from now to 2040, we'll probably start seeing power stations start to close, and then we won't be able to obtain that much virgin fly ash, and that's why we'll have to look at alternative binders such as dam ash.
Yeah, thank you. And perhaps a question for the both of you, because you're both looking at new technologies, like how, in terms of cost, can you comment? So like in terms of the use of green methanol in cement manufacturing, is it going to increase the cost of cement? The same goes for carbon capture in RCA. So this carbonated RCA, is it going to be more expensive than say a natural aggregate? I'm not sure if you're in a position to talk about this now, but if you could make some comments in terms of this implications as well.
Well, I'm definitely I don't have the actual numbers in terms of how much our recycled aggregate is going to cost. But it's I think the aim of the objective of this project is more of how can we minimize our CO2 emissions, and how do we pass that reduction of CO2 embodiment in the final product onto our customers. And I see there's a value in itself where if we're able to pass that on, then we all as an industry can reduce our carbon footprint. And also the process. So like I said, mentioned in the presentation, if if there isn't a process like recarbonation, what we're doing here is a lot of the recycled material gets find its way into landfill, and they essentially become a byproduct or waste. And recarbonating definitely upcycles, it gives as value back into this byproduct and divert it from waste. So we are also using flue gas, redirect flue gas, which is another byproduct from the cement manufacturing process. With any process, I mean, there will be initial investments, but it's hard at this point to give a monetary value to the final product, considering the amount of CO2 that we were able to reabsorb out from the atmosphere, especially from our cement manufacturing process. And because we're always going to have waste, I see this as an ongoing method for us to capture CO2.
Thank you, Jerry. And then Olivia.
So I can't give you figures regarding cost, but what I can say is that we'll be able to offset the production by selling to Mitsubishi the CO2, but also because of the amount of CO2 that Mitsubishi would need in order to produce green methanol, we'll actually probably have to look at investing in maybe a new kiln in order to produce more clinker in order to produce more green methanol. So unfortunately, although I can't provide you with cost, I can say that there will be that we'll be able to offset that. So there shouldn't be an increase in GP.
Yes, at this point, I'd like to thank you both again. For all of our other attendees, if you have more questions, please feel free to contact Jerry and Olivia directly. Again, thank you very much for your time in attending our webinar, and thank you to Jerry and Olivia. And I'll hand it off now back to John to officially close our webinar. Thank you.
Thanks, Josh. And ladies and gentlemen, can I ask you to join with me in thanking our two speakers, Jerry Fu and Olivia Alexis, and our two young professionals, Josh Tappis and Sophie Maguire.